So today we're going to start talking about X-ray diffraction, or XRD. And we want to look at XRD because it's a very effective way to determine crystal structure of materials, what we've just been talking about with crystal symmetry and crystallography. So this is our method for determining those crystal structures. And so we can identify compounds from their crystal structure, but this isn't giving us information about its composition. It can give us clues to it, but this is really talking about its crystal structure, not its composition. So that's an important distinction to make. So we've already discussed diffraction in terms of light. Well, the principles are really the same with X-rays, and also very similar for electrons and neutrons, right? So the same sort of principles apply. We're just looking at different wavelengths. So that's another thing to keep in mind. We'll also, in this discussion of X-ray diffraction, kind of limit our discussion of X-ray diffraction to what we call spectroscopic. So basically a spectrum of scattered intensities. And you'll see examples of this when we get to the applications. There are other sort of photographic methods that you can read about, but we're going to stick to the spectroscopic in our discussion. And the first thing I want to talk about in the field of X-ray diffraction is how we get X-rays. How do we generate X-rays so we know what type of X-rays that we have? All right, so first of all, X-rays are a form of EM radiation. So that's electromagnetic radiation. They have short wavelengths, but high energy. All right, so we can produce X-rays by rapid deceleration of charged particles. So in most cases, this is electrons. All right. So typically, X-rays generated in the laboratory setting by a tube. So a tube design. And let me switch over to the slides and show you that tube design. All right, here's a figure from our book, figure 2.1, and it shows the X-ray tube design that is fairly common. And so we start out with the filament. The filament is contained within a vacuum tube, hence the tube. So this whole thing is under vacuum. So we have a filament, and that filament is a high voltage is applied to that filament, just like an old-fashioned filament in a light bulb. And when that high voltage field is applied, the filament is heated, and electrons are emitted from the filament tip. So we have these electrons, and they are accelerated. So we have a voltage. So we have basically a charged region. So these electrons are accelerated at a metal target, which we also call the anode. So this metal target is, again, a metal. Typically, you'll see a lot of studies where it's going to be copper, but it may also be molybdenum, and there are other examples as well. But the most common by far is copper. And so when the electrons basically hit this target, they are decelerated, this rapid deceleration that we talked about, and it enables the conversion of these kinetic energy of this electron to be converted to the high energy of X-ray radiation. And so that's the process we have. And there's also a cooling system because these things can get very hot in this design. So important cooling system. And in fact, our own system has recently been down because the cooling system was down. All right, from the tube design you just saw, you can see that a certain voltage is applied to accelerate the electrons that then slow down at the target. And so our the wavelength of the X-rays we call lambda, and this is related to the accelerating voltage. And we call that V. So the wavelength is equal to 1.2398 times 10 to the 3 over the voltage. And this is in units of nanometers with this constant that we have up here. So the wavelength is inversely proportional to the voltage. All right, a little bit more about that tube design. You saw the cooling apparatus on the design. And so X-ray tubes convert most of that kinetic energy. So this is the kinetic energy of the electrons to heat. So that's why they get so hot, because most of this is converted, most of that energy is converted to heat, and only around 1% is converted to X-rays. So it's not very high efficiency. But this also shows you why the cooling is required. All right, so these X-ray tubes generate a range of wavelengths. And they start with a minimum wavelength. And so this is also known as the short wavelength limit, or SWL, sometimes abbreviated. And when you have this continuous X-ray, we sometimes call that white X-rays, because that's similar to white light, right? It contains a lot of wavelengths, not just one. So sometimes that's referred to as white. Okay, so let me sort of draw you what these spectrums often look like. So on the y-axis, we're going to have intensity. So this is X-ray intensity. And then on the x-axis, we're going to have wavelength. So I'll just put that as lambda. And so on the short wavelength, we have that limit, right? So effectively, let's say that that's our wavelength. Or let's start with the lowest voltage. So the lowest voltage gives us the highest wavelength. So if we look at 5 kilovolts, this is the short wavelength limit, and then it increases in intensity after that. If we increase the accelerating voltage, it decreases the short wavelength limit. And so it maybe starts over here, increases, and then it kind of plateaus out. And we're going to have curves that look like this. So this is 10, 15, 20. And so at 20 kV accelerating voltage, that short wavelength limit is about 0.069 nanometers, just kind of for a reference point on this plot. You can also find this plot in our course textbook as well. All right. And when we get to even higher, we start to see an interesting phenomenon. So it might look like this. So this is 25. So at this higher accelerating voltage, we start to see some deviations from this more continuous wavelength or white radiation. So that's important. So these sharp maxima we have, they appear at specific values that you see of the wavelength, and so these have characteristic energies or wavelengths, and these are what we call characteristic X-rays. So that's what we're going to talk about next, is these very specific sort of peaks on this more continuous curve, because these characteristic X-rays are going to be of use for us in diffraction studies.